everyone, I am Chandrika from the Department of Electronics and Communication Engineering at Srinivasa Ramanujan Institute of Technology. Today I am going to present my continuous alternative assessment 2 on the subject of digital circuits and designs. The topic of my presentation is the designing a 4-bit up-down counter using for loops in Verilog. In this session, I will explain how to design a 4-bit up-down counter using for loops in Verilog. Contents: Introduction, Objective, Counter Basis, Why use for loops in Verilog, Block Diagram, Verilog Code Part 1, Verilog Code Part 2 using for loop. Test bench design using for loop, simulation waveforms, results and observation, conclusion, future work and enhancement references. Introduction: Designing a 4-bit up-down counter in Verilog using for loops provide a structured and efficient way to implement the counter's logic. While for loops are more commonly associated with test benches or synthesized blocks for repetitive operations like array initialization, they can also be used within always blocks for sequential logic, though care must be taken to ensure synthesizable constructs. While for loop are common in software programming for iterative tasks, their application in synthesizable Verilog code for hardware design, especially for creating a simple counter, requires careful consideration. In Verilog, for loops are primarily used in test benches for simulation purposes or in generate blocks for repetitive instantiation of hardware components. For a direct behavioral description of a counter state changes, a simple if-else structure with an always block reacting to clock edges and control signals is typically more straightforward and directly translate to efficient hardware. The for loop strength lies in its ability to parameterize and replicate design elements, which can be particularly used for creating counters of arbitrary bit widths for generating repetitive logic structures, thus offering a powerful tool for scalable and flexible hardware design. Next one is objective. The objective for designing a 4-bit up-down counter using for loops in Verilog, suitable for a single slide. It is to demonstrate and the implementation of a synchronous 4-bit up-down counter behavioral logic using Verilog loop construct within an always block for sequential circuit design. This object highlights functionally a 4-bit up-down counter capable for incrementing or decrementing its count. Implementation method: utilization of Verilog for loops. While for loops are more commonly used in test benches or for generating repetitive structural elements in synthesis, this object focuses on their application within behavioral modeling for conceptual understanding. Next one is Verilog construct, especially targeting the for loop within an always block, emphasize the sequential nature of the counter, educational value, illustrating a specific Verilog coding style and its application in digital circuit design. Next one is counter basis. A 4-bit up-down counter increments or decrements a 4-bit binary value from 0 to 15 or 15 to 0 based on the control signal. In Verilog, this can be implemented using behavioral modeling within a always block triggered by a clock edge. Key components: inputs, clock signal typically triggers state changes on its positive edge. Reset: asynchronous or synchronous reset typically sets the counter to 0. Up down is control signal determines counting direction. Example: 1 for up, 0 for down. Output: count 4-bit register holding the current count value. Behavioral logic: reset: if reset is active, the count is set to 0. Counting: otherwise on the positive edge of the clock. If up down is high, count increments by 1. If up down is low, count decrements by 1. Why use for loops in Verilog? Using for loops in Verilog for designing a 4-bit down counter While possible is not the most common or idiomatic approach for describing the core counting logic. However, they can be useful for parameterization and generating repetitive structures. Genericity and parametericity. For loops enable the creation of generic designs that can be easily adapted to different bit widths without rewriting the entire code. For example, you could use a for loop to instantiate multiple flip-flops or logic gates for each bit of the counter, making it straightforward to change from a 4-bit to an 8-bit counter by simply changing a parameter. Code reusability and readability. When dealing with a repetitive structures, for loop reduce code duplication, leading to more concise and readable Verilog. Instead of explicitly defining the behavioral for each individual bit, a loop can be captured the pattern and all apply it across all bits. Test bench generation. While not directly part of the counter's design, for loops are extremely valuable in Verilog test benches for generating stimulus, checking outputs, or performing repetitive tasks during simulation. This allows for the efficient verification of the counters functionally. Block diagram. This is the 4-bit up-down counter. The inputs are the clock, reset, up-down. Output of the count 3 is to 0. Signals. Clock input drives the counter. Reset signal resets the counter to 0. Up-down control signal. 1 for the up counting, 0 for the down counting. Count 3 is to 0. 4-bit output showing the current counter values. Verilog code part 1. Verilog code. This is the code of a Verilog code. Module up down counter. Input clock reset, input output down. Output raise the 3 is to 0 count. Clock is the clock signal. Counter state changes on the positive edge of this signal. Reset. The reset signal when asserted the counter is reset to 0. This is typically asynchronous if it's in the always at the rate block, or synchronous if only positive click on the sensitivity list and the reset condition is inside in the block. Up down, a control signal that determines the counting direction. If up down is high, the counter increments. If the up down is low, 0, the counter decrements. Count. A 4-bit output register that holds the current count value declared as a reg because it is value is assigned within an always block. Verilog code part 2. Using for loop. Show behavioral block with the loop logic. This is the Verilog code. Note: for loops are not needed in simple counter logic but can be used in extensions. Examples: multiple counter test bench initialization. Test bench design using for loop. Example: use of for loop in test benches to simulate behavior. Initial begin for I equals to 0, I less than 20, I equals to 1 plus I plus 1 begin. Useful for automating clock or stimulus generation. Simulation waveforms. When simulating the above test bench in tools like ModelSim, Vivado or GTK Wave, you should see. On reset, count is set to 0000. Count increments from 0000 to 1111. 0 to 15 when up down is 1. The count decrements back down is 000 when up down is 0. The waveform for count will look like a sawtooth wave going up and then down. Waveforms. Results and observation. If one were attempt to use a for loop within always block to describe counters behavior, the synthesis tool would be likely unroll the loop. This would be result in a large unoptimized combinational circuit if the loop iterations were meant to represent sequential steps, generate warnings errors. The synthesizer might issue warnings about non-synthesizable constructors or infer incorrect hardware, produce incorrect functionally. The resulting hardware would unlikely behave as a sequential counter, as the inherent sequential nature of a counter is best described using registers and conditional logic within an always block. In summary, while for loop have their place in Verlag for specific design and the verification tasks, they are not the appropriate construction for describing the sequential logic of a counter that realizes on state changes over clock cycles. Behavioral modeling with the always block and if else statements is the standard and correct approach for synthesizing sequential counters. Conclusion: the use of for loops in Verlag for designing a 4-bit down counter is generally not the most common or recommended approach for describing sequential logic like counters, especially when targeting synthesis for hardware implementation. While for loops are powerful construct for generating a repetitive code in Verlag, their primarily application in counter design is typically for generating instances of identical submodules or for a parameterized designs. Rather than directly implementation, the counter state transitions within a single always block. Future work or enhancements. Parameterization of scalability. Generate bit width. Modify the counter to be parameterizable for any n bit width rather than a fixed at 4 bits. This is would allows reuse the same code for counters of different sizes. Asynchronous load preset. Load functionally. Add an input load and an data input to allow loading the counter with a specific initial value asynchronously independent of the clock. Preset functionally. Similarly to load the but often use to set the counter a specific value at reset. Output flags and control signals. Terminal count TC output borrow carryout enable to hold functionality. References. Designing a 4-bit up-down counter in Verlag using for loops is not typically a recommended approach for the synthesizable hardware description. For loops in Verlag are primarily used for test benches and generate books combinational logic. Thank you.